So, last of the lectures on dynamical systems. So, this is just to show you what we have done so far. So, on the first day we looked at phase space and trajectories, just a you can say revision of the concepts. Then geometric way of thinking about dynamics and differential equations, which is typically we are looking at a first order differential equation du dt equal to f of u. Then we looked at fixed points, which is defined like this. Then the stability, which is determined by the slope of f at the fixed point. Then we looked at numerical, so that was the first day, and then we looked at numerical methods for solving differential equation, in particular the Euler method, and then we looked at the various bifurcations for the first order one dimensional dynamical systems. And then yesterday we spent almost the whole lecture looking at imperfect bifurcations or catastrophe. So, all of this had one thing in common. They were looking at one dimensional systems, okay, or in other words we are looking at a single first order differential equation where u is a scalar variable. Okay. So, today depending on how much time permits, we will look at high dimensional systems. So, we will start with two dimensional systems. So, this means that we will have two equations du dt equal to f of u v and dv dt equal to g of u v. Okay. So, we will be looking at equations of this type. So, first we will look at linear systems and we will see that what kind of behavior these are capable of. Then we will look at a few examples of nonlinear two dimensional systems. In particular, we will look at something which is very familiar to many of you, prey-predator system. So, we will first look at the trivial example of Lotka and Volterra, and then we will make it a little more realistic. So, this is what is known as the Rosenzweig-MacArthur model. Both are models of prey-predator, but one is for mathematicians, the other is when you want to actually speak to ecologist. Never ever talk about Lotka Volterra with the ecologist, never hear from that person again. Okay, and then we will see how you can take this and actually start applying in different areas. So, for example, the same prey-predator kind of model could be used in economics. I am sure Aninda would have a few expletives to say when I actually do it.
Actually, I have a paper doing that. So I am sympathetic to this.
Okay. Called the Goodwin model. I will not go into the details of this. I will not try to derive it because we simply do not have enough time, but just to show you analogically, how a prey-predator model which arose in ecology can be used to also talk about economics. Then we will apply it to history. So, this is part of what is known as cliodynamics or cliodynamics. So, Clio, as you know, is the muse of history, and Peter Turchin, an ecologist, came up with this name that what if we use the dynamical systems of the kind we use in ecology and apply it to understand historical processes. So, he has several books written on this. So, so this is a model of Turchin of how states rise and fall. Okay. So, I will call it Turchin's cliodynamic model. Now, I will be cheating a bit because it is actually 3 variable, okay. It has a third variable, but the basic idea is based on Lotka Volterra. Okay. And as I will mention that Turchin is only one of several people who have had this brilliant idea. There is another very nice paper which looks at Easter Island's rise and fall. So, anybody hasn't heard of Easter Island? Okay. So, Easter Island is this remote island in the Pacific which is very far from either the Southeast Asian islands of Indonesia, Australia and so on, also very far from South America. So it's somewhere in between. It's currently, I think, part of Chile. So the puzzling thing is when Europeans first visited this island, they expected it to be unpopulated, but they actually found humans living there. Not only that, they found this enormous stone sculptures. Okay, so I'm sure even if you don't know the name Easter Island, you might have. Sorry, this keeps falling off. So you have seen this huge stone monoliths. Okay, they look something like this. So there are rows and rows of this. Okay, like this, standing on the volcanic plateaus. Okay, and it's pretty clear that these were built by a society which had enough what do you call, extra money, surplus, to be able to actually put people to work on carving these, then taking them somewhere and putting them up, because they were not put up where actually they curved it. So you have to transport this huge monoliths and put them up there. And so from this is like one of the many archaeological evidence which shows that around 1200 AD they had an extremely rich civilization. But when the Europeans went there, it just was a village subsistence economy. And when they asked these people who were living there who made this, they said the gods did this. So they had no idea, you know, there's no continuity. And so the question is, how did this small island have a civilization rich enough to do this and then collapse to a point where, you know, the people have absolutely no idea, you know, that their ancestors did all this or how they did this. Okay, they even have, by the way, written language which is still undeciphered. So they have, this is the Rongo script. So the civilization civilization essentially regenerated to such a point that the 19th century 19th century population of this island had already forgotten writing. Okay, so it's still one of the undeciphered scripts actually. So people have no idea what this Rongo script actually.
Tanikan gave an answer.
Yeah. We are not talking about Tanikan. Yeah. So so actually, so there's a very nice paper I've read which actually gives a Lotka-Volterra type model to this kind of Easter Island phenomenon. There's another very nice paper which looks at the history of China from the point of view of Lotka-Volterra and says that, so in China you have this very clear kind of oscillations where you have this rise of the, you know, starting from the Qin Empire to the Tang Empire, Ming Empire and so on, and then in between you have this civil wars where the entire country breaks up into small fiefdoms and so on. This has happened, you know, at least 7 times. So why this happens with almost cyclical regularity? So people have argued that, well, you can think of it like a Lotka-Volterra system where population and resource are like the 2 variables which are kind of competing with each other. Okay, so its ambit goes far beyond the original context of ecology in which it was devised. Okay, and then so I am being very ambitious. I don't think I have enough time to do all of this, but let me just try anyway, and then if time permits I will go to describe something known as Hopf bifurcation, because 2-dimensional system, and this is what I will actually start with, is capable of a behavior which 1D systems are not capable of, which is oscillations. Okay, and so the bifurcation which leads from a fixed point to an oscillation is a Hopf bifurcation. Okay, so we will look at this Hopf bifurcation, and there is a theorem associated with it which is named after Poincaré and Bendixson. I won't do the theorem, just tell you that if you want to show that a particular 2-dimensional system is capable of oscillation, how to show that? Poincaré-Bendixson theorem gives you some ideas. Okay, and finally I will go to a 3D system. So, you know, even if I don't manage to do all of this, you at least I am giving you what I plan to do, so that at least you can go and look it up. I will use a model called the Hastings-Powell model. By the way, these papers are already uploaded in the web page under my thing. So, you can actually look up these papers. Hastings-Powell is uploaded, the paper of Turchin is also uploaded, and another couple of papers are uploaded which is related to this linear two-dimensional systems. So, Hastings-Powell model is basically of a 3 species food chain. So, the Lotka-Volter is basically you have prey and you have predator, right, and so the prey is being eaten by the predator. So, you are giving resource to it. Now, the Hastings-Powell model says what if there is a super predator, something which is preying on the predator. Okay. So, you have now a 3 variable 3 coupled differential equations, okay. And suddenly you see a completely different kind of behavior, chaos. Okay. Now, you can think of chaos in many ways. Some people say okay, it is irregular, unpredictable behavior and so on. Technically what we mean is sensitive dependence on initial conditions. Or the so called butterfly effect. So, we will look at what this means, but 3D is very hard to work with. So, what we will do is instead of looking at differential equation, we will look at difference equations or maps, because for maps even a one dimensional map is capable of showing chaotic behavior, and we will look at one particular one dimensional map which is the difference equation analog of the logistic equation called the logistic map. So, this will be defined as xn plus 1 equal to r into xn into 1 minus xn, where xn is the ratio of the population to its carrying capacity, the maximal population that a population can that a ecosystem can hold. Okay. So, this we will see is capable of showing chaos, and then we will introduce a very important quantity known as Lyapunov exponent, which measures this, how sensitively the system is dependent on initial conditions. Okay. So, this Lyapunov exponent, if it is positive, that means the system is chaotic, and depending upon how large positive it is, the more chaotic it is, the more sensitive it is to small variations in initial conditions. So, this is how you quantify the degree of chaos in a system, okay. And we will end at that point. Okay. So, let us see how far we can go. All right. So, 2D. Okay. So, first let us look at a linear system of 2D equation. So, what is the most general one I can think of? Du dt equal to, so what is the simplest linear equation I can write? Sorry? Arey, nah, constant is like very trivial. Yeah, so AU plus BV dV dt equal to CU plus dV. Okay. So, the evolution of both u and v are linear functions of u and v. Okay. Now, the sign of this A, B, C, D can change. Okay. That I am not saying anything about. All right. So, how do I analyze this system? What kind of behavior is this capable of? Okay. Now, what are the fixed points? So, how do we find fixed points? You said du dt equal to 0, dv dt equal to 0. So, you get the linear equations AU BV equal to 0, CU plus dV equal to 0, right, and then you solve for u and v. So, what will you get? So, you will get some expression of u in terms of v, then you plug this in okay, here, and you solve for V. Okay. So, instead of exactly solving it, let us call them U star and V star. Okay. So, for U equal to U star and V equal to V star, this holds true. Okay. Okay. So, that is we have found the equilibrium. Now, what can we tell about stability? How do we find out about the stability? So, you remember that when it was du dt equal to f of u, so first you found out u star, which is basically f of u star equal to 0, and then you found out stability by looking at del f del u at u equal to u star. Okay. So, if this was positive, that meant it was unstable, and if it was negative, it meant it was stable. Okay. So, that is how you find stability. But how do we now find stability for a 2D system? Any ideas? So, you have FUV and you have GUV. Yep, partial what? Of sorry, F and G with respect to
U and V.
So, how many such partial derivatives can we get?
4.
4. So, how do we use those 4 to find out the stability? You are right. So, we can get del f del u, del f del v, del g del u, and del g del v, and we can evaluate them equal to u star, v equal to v star. But how will that tell me about the stability? Wonderful. Yeah. So, I can't just individually look at them and say anything that's true. I have to ask, okay, so suppose I look at the matrix del f del u, del f del v, del g del u, del g del v, evaluated at e equal to u star, v equal to v star. Let's call this matrix J. I call it J for a particular reason, because later on we will see that for the nonlinear system, when I linearize, this is called the Jacobian. So, I got a 2 by 2 matrix. But from here, how do I find out the values which will tell me about the stability? Okay. So, this is where your eigenvalue and eigenvector comes in handy. Yeah.
Is it a good idea to just plot G and F on the UV plane and then look at
Yeah, but the problem is we are very bad at getting a sense of a 3D surface, and then you also not only have to look at how.
there are 2 3D surfaces.
Yes, I mean that's also there, right? You have 2 3D surfaces, right? So simultaneously looking at 2 3D surfaces and figuring out what will happen is something our human vision is not very good at. We can do it with a single 3D surface. We can say that, okay, this is a hill, and so the slope over here is negative, but then we are looking at 2 simultaneous things.
Look at the contour lines of G and F.
Sorry?
UV plane, contour lines of G and F.
Yes, but simultaneously doing it and comparing is often very difficult. Okay, so that's why. Okay, but
One possibility is, along with doing this analytical approach, sometimes we follow is to just plot the phase space
yeah,
on UV plane.
Hmm.
So in that case, you are not having the chart dimension. So just
yeah. So very good point. But that's like plotting trajectories. Okay,
yeah, I mean this is the starting point.
Yeah. so that's like plotting trajectories. Very good. Yeah. So that's why you have eigenvalues and eigenvectors. Now, sometimes we just plot, like we use that as a entry level exam in our institute. We give them some arbitrary 2D matrix. Ananta is smiling. Did we ask you that? Yeah. 2 by 2 matrix and say what are the eigenvalues and eigenvectors. Now, how do you, so maybe most of you know how to calculate eigenvalues and eigenvectors, but what is the intuition behind this? The intuition is this, that take a sphere, okay, or a circle, and you apply a transformation, let us say this transformation. So, you apply it on this circle. So, this circle is basically a series of points, and you ask, as a result of applying this transformation, how does it change shape? Okay. So, if it becomes an ellipse, okay, so that means along this axis it has increased by this factor, and along this axis it has increased by this factor, then you know, so basically it has multiplied by 1.2 times, and here it has multiplied by 1.5 times, then this is pretty simple. So, you know that this, what this means is that the matrix is simply this. So, along sorry, I should say 1.5 and 1.2. Along the x axis you have made it 1.5 times larger, along y axis you have made it 1.2 times larger. Okay. So, this is a diagonal matrix. Okay. The diagonal elements are finite, the off diagonal elements. So, that means along x axis and along x axis and along y axis, what happens is only linked to this multiplier of the x and the multiplier of the y. But suppose it looks something like this. All right. So, it means that you now also have contributions of the expansion along x from y and the expansion along y from x. So, these off diagonal elements would be some finite quantities. Okay. So, in fact, you look at cos theta sin theta, you can take the projections. Okay. So, that essentially is how to visually think of this eigenvalues and eigenvectors. So, that what you are doing is, then you are redrawing your, coordinate frame such that along this coordinate frame you can again think of it as if that the one multiplication is along this and one multiplication is along this. So, you are just changing your coordinate frame. So, the eigenvector is nothing but the rotated coordinate frame in which again it will become a diagonal such that along this new x axis and new y axis only you will get this multiplicative factor. Okay, so, that is the intuitive or pictorial way of thinking about eigenvalues and eigenvectors. Okay. So, now let us come to this. So, let us call them A, well actually not let us call them, we already know what they are. They are A, B, C and D. Okay. And since they do not depend on U star V, B star, V star, C star, okay. So, we know it is around 0 0 that this is happening. Okay. Okay. So, how do we find eigenvalues? Well, if you know it, fine. If you do not know it, it is simply this. The eigenvalues, there will be two eigenvalues for a 2 by 2 system. So, let us call this unknown thing lambda, and I will evaluate the determinant A minus lambda B and C D minus lambda. This comes from the fact that I am trying to solve J minus I, J minus I lambda. Okay. I am basically solving this. Okay. So, what do I get? A minus lambda, so this is the determinant, D minus lambda minus BC equal to 0. From here I get lambda square equal to A minus D lambda minus BC. I collect terms, so lambda square minus, oh sorry, I missed out on something. This is AD minus BC, sorry, plus AD minus BC. Yeah. Yeah. So, what is this? Yeah. So, what is this AD? So, look at this. What is A plus D? It's the trace, right? So it's the trace of j lambda. Sorry? Oops. Sorry. Yeah. So this AD comes from this factor. Okay. Yeah. And what is AD minus BC? Is the determinant of j, right? So what is this? This is a quadratic equation in lambda, right? Where this is, so this can be thought of as a x square or ax square plus bx plus c equal to 0, where a is 1, b is minus 1 and c, b is minus trace of j and c is determinant of j, right. So what are the solutions? So lambda 1, 2 are minus b plus minus square root of b square minus 4ac divided by 2a, right. So that means minus of b is minus of minus trace j, so that is just trace j plus minus root over trace j whole square minus 4 times determinant j divided by 2. So those are the eigenvalues. So if you know in the linear system, just by knowing the coefficients, just by evaluating the trace and the determinant, you know what are the eigenvalues, and once you know the eigenvalues you can also determine the eigenvectors. Okay. But without actually having to solve it, I can actually say just from knowing the trace and the determinant how the system is going to behave. How? So consider the system. What if lambda 1 and lambda 2 are both negative? What will happen? So if you look at as so this is your u, this is your v space, this is your fixed point. So if you start from somewhere very nearby, what will happen? Which way will you go? Both are negative. So if the slope is negative, what happens? You go back towards the fixed point. So basically it tells you that you will have something which looks like this. Okay. So this is known as a stable node. So your fixed point 0 0 would be stable in the sense no matter how, which direction you give the perturbation in, it will just flow back. Okay. What if lambda 1 and lambda 2 are greater than 0? Oh, there is one possibility. So this is there is a possibility that you could have complex eigenvalues. Okay. So here I am saying that let us suppose that these are real. Okay. We will see what happens when they are complex. Okay. So if it is real, so that means they are flowing out. So this is an unstable node. Okay, now comes the interesting part. What if one of them is positive and one of them is negative?
Come in direction of eigenvector.
So it will come along one direction and go away along another, right? So you have the possibility that this is a stable direction, this is an unstable direction. So you will approach the fixed point along one direction and go away in another direction. So this is known as a saddle, because in our intuition we know that if you have something like a horse's saddle, then if you take a marble and you start from here, it will start rolling downhill, but then because it's shaped like this, it will also simultaneously go away. Okay. So it approaches along this point and then goes away along this direction, right? Yeah.
Stable node,
Yeah.
lambda 1 times lambda 2 should be positive, right? Both are negatives.
Both are negative.
And
Yeah.
the sum would be negative.
Sorry, why
Stable
should
node
some be negative? No, I didn't understand.
So lambda 1 and lambda 2,
Yeah.
if both are negative,
Yeah.
the product will be positive.
There's a comma in between.
It's a comma.
There's a comma. Lambda 1 greater than 0, lambda 2 greater than 0. It's not the product. So individually. So I'm saying that what would happen if they're individually both positive? Yeah, what is your question?
So, like a saddle is like stable along one eigenvector.
So it has what we call a stable manifold and an unstable manifold.
So, but in the literature, often saddles are just described as unstable. Right?
Yeah, that's because eventually what will happen? You will go away.
As if you're in that direction, you will come.
No, but even the smallest perturbation is going to throw you out. So you approach it very closely, but eventually when you come sufficiently close, you will always go away. Okay. But what you are saying is an interesting point. So in chaotic systems, so there is something called chaos control, which, as some people have said, it's an oxymoron. Right? Actually, the person, Bill Ditto, was giving this lecture and he said, I was giving this talk in China and I said chaos control is an oxymoron, and I could see immediately people riffling their Mandarin English dictionary to see what's an oxymoron. And so then, to make it easier for them, I said an oxymoron is when you have two contradictory things together, like military intelligence. And he said that one section of the crowd immediately became completely silent and the others started laughing. So, you make your inference what those guys were. So, yeah, so in chaos control what we have is, we have tons of saddles. Actually, we have infinite number of saddles, okay, and the whole idea is how do you alter the parameters of your system so that you constantly keep shifting the parameters such that you are bringing the trajectory very close to this stable manifold. Okay, so it's like trying to shift, like trying to hold the upright thing. It is like when I'm moving around, what I'm trying to do is I'm constantly trying to take my system along the stable manifold. Okay, so the whole chaos control idea is you keep shifting your system such that you're always trying to put the trajectory on the stable manifold. You know that you can't ever make it exactly on the stable manifold, so it will eventually go away. But if you can indefinitely keep doing this, it will stay very, very close to this unstable point. Okay, so that's the whole concept of chaos control actually. Okay, but yeah, in reality, of course, if you have a saddle, because it will always eventually go away, that's why it's called unstable.
So, does it have to do with the dimension of the stable and unstable manifold?
No, because if there is even a single unstable manifold, when you come close enough, eventually this unstable manifold is going to take you away. Okay.
Can I just make a
Yeah.
pedantic point here?
Yeah.
So, saddle path also has the name. This particular type of stability is also called saddle path stability. In the sense that there will be only one line. So, probabilistically it's 0 mass. But there will be one line along which, if you are there, you will be moving along the stable path. Everything else is unstable. So its saddle path is not always thought of to be, mathematically it's not all unstable. There is at least one path which is stable. But finding that is very difficult. But the point that I wanted to make is that saddle path is not always a description of instability. There is actually a terminology which calls it saddle path stability.
Okay, so now I know that there are also other possibilities, like your eigenvalues can be complex. Why? Because this thing inside could be a negative number, right? So you could have something like a plus, or sorry, not a, p plus iq and p minus iq could be your eigenvalues. Now, how will I talk about the trajectories? So, suppose p is equal to 0. So, you have only plus iq and minus iq. What will it be? It's a circle, right? So, basically you have, because there is only a sine cos kind of behavior. Okay. What if p is real? So, if p is real and it is positive, what will you have? So, there is a cyclic component, but in addition because P is positive, this it's also going outward, right? And so you have something which is spiraling out. And similarly when, so this is when P is positive. Similarly when P is negative, and this is when P equal to 0. And when P is negative, you have something which is spiraling in. Okay. So this is called a stable, unstable spiral. This is called a stable spiral, and this is called a center. Okay. So that's more or less what you can have in a 2D linear system. You can have a stable node, unstable node, saddle, center, an unstable spiral and a stable spiral. Okay. Now of course you can evaluate the eigenvalues and do this, but can I just have a quick handy reference where I just have the matrix and just evaluating trace and determinant I can work out what behavior it will be. So I can do something like this. I can say, look, this is my trace of j axis, this is my determinant of j axis. Okay. Now when is it complex? When trace j whole square is less than 4 determinant j. So the trace j whole square equal to 4 determinant j, that what is it? Shape, it is a parabola. Okay. So trace j whole square equal to 4 determinant j. So if you think of trace j as x and determinant j as y, it is a y equal to ax square form, right. So it is a parabola. So this is trace j whole square equal to 4 determinant j. So inside this the eigenvalues are complex because trace j square is less than 4 determinant j. Here the eigenvalues are all real. Okay. So what will you have here? So remember, so since trace j is positive, that means what? Here P is greater than 0, so you are spiraling out, right. So here you have a stable spiral, here you have unstable spiral. What will you have on this y axis line? It is P equal to 0, sorry, center, right, because you only have imaginary. Okay. What will you have on this side? The eigenvalues are all real and they are positive. Stable node, unstable. And what will you have here? Stable node. Okay. Now, so this is all for determinant j positive. What will happen if determinant j is negative? It is a saddle. Sorry? Oh, I am so sorry. Yeah, you are right. This will be stable spiral. Sorry. This will be stable spiral and this will be unstable spiral. Thanks. So this is this is this, center is this, stable spiral is this, unstable spiral is this. Now when determinant j is negative, what will you have? That means the two lambdas are of opposite sign, okay, and so you have the saddle. All right. So once you know j, just by evaluating its trace and determinant, you can work out which of the behavior it will be. Okay. Now let us take an example. Okay, and for once I am not going to take an ecological example because to get to ecology I need to do nonlinearity. I will use an example from Strogatz's book. It is called types of love. Okay. So, for our purposes we will take two lovers, let us call them Romeo and Juliet. I know it is non-diverse in today's world of XE and so on, this is supposed to be very politically incorrect, but I am an old fashioned guy. Okay. So, let us take Romeo and Juliet. Alright. So, first let us take the case of dr dt equal to aj and dj dt is equal to minus br. Okay. Pictorially I can represent like this. So, what is R? R is Romeo's love for Juliet and J is Juliet's love for Romeo. Okay. If it is positive, that means the corresponding person loves the other person. If it is negative, that means the corresponding person hates the other person. Okay. So, you can think of it as this R and J, and so this interaction can be thought of that there is a link. So, this is basically how you can turn it into a network picture. So, R is motivated by, let us say, Juliet's love for him with a strength A. Juliet on the other hand is repelled by Romeo's love for her with a quantity B. Okay. So, you might think, okay, this is pretty strange. Well, this is the so called fickle lover syndrome. So, in other words, Juliet likes to be admired, right, but too much admiration she gets turned off, right. So, when Romeo's love for her is kind of gradually rising, she gets scared and starts being very haughty. At that point Romeo is kind of gets turned off and stops giving attention, and then Juliet gets really worried and then starts showing affection. Okay. So, what will happen? Use your two-dimensional analysis. What is the outcome of this affair? Sorry? Okay, let us look at the matrix. What is the matrix? So, 0, okay, A minus B 0. Trace is 0. What is the determinant? Okay. So, what behavior did I wipe the, no, here. So, it is here. So, what will happen is a never ending cycle. Okay. So, this is Romeo and this is Juliet. Their love for and hate for each other is constantly waxing and waning, out of phase. Okay. So, you can imagine the consequences. Okay. But this is like very dull, right? I mean, because I am not using the diagonal elements. So, let us look at something a little more interesting. I am really sorry, Anindo, I mean I am really eating into your time. The fact that you do not even say it is alright means that you are really getting angry.
I was thinking of responding, I will eat into the eating time.
Right. Okay. Now, let us take this example. Okay, so the most general form that I can take is this, where I just call this A, B, C and D. So, in other words, the general form is dr dt equal to AR plus BJ, dj dt equal to CR plus dj, And now just by changing the sign and the magnitude of A, B, C, D, I can look at different styles of love affairs. Okay. So suppose we take the form where, okay, and we can do something. We can say that these are the magnitude wise they are identical lovers. Okay, so in other words, C equal to B and D equal to A. This is just for simplicity. Okay, so this means that dr dt would be AR plus Bj. I mean, you don't need this, I am just doing it for simplicity. Even without this, you can do it. Br plus Aj. Okay. Now, suppose A is positive and B is positive. Okay. Now, Strogatz says that one of his students called this style of a lover an eager beaver. In other words, they are not only stimulated by by the other person's affection for them, they are also in love with the whole concept of falling in love. Okay. So they just oh, I'm in love, I'm in love, I'm in love. It's like Tom Cruise in that show, infamous show, like jumping around, right. So so what will happen? So what is the matrix like? A, B, B, A, and all are positive. Anyone? Sorry? I can't hear you. Sorry? Sorry, who was saying it? Can you just raise your hand? Oh, Anand. Huh? Same what? So what would the behavior be like is my question. So just look at what is the trace and what is the determinant. Yes. Can you make it little more detailed? So trace is 2A, which is positive. What is determinant? A square minus B square. Okay. Is it an unstable node or is it an unstable spiral? But A and B, regardless of what their values are, they can't be imaginary, right? It's A square minus B square. It has to be real, right? It's either positive or negative, right? So 2A is greater than 0, so that means you are on this side, okay? But the determinant could be positive or negative depending upon if A square is greater than B square or A square less than B square. So if it is positive, what happens? You have an unstable node, and if A square is less than B square, you have saddle, right? So actually you can work out the eigenvectors also. So the eigenvectors for the case where you have
But this can also be a spider, right?
no, it can't be a spiral. How can it be a spiral? There are no complex eigenvalues. Okay. So if A square is greater than B square, so you can show that the eigenvectors are simply these. Sorry, what am I doing? Yeah. Yeah, sorry. And the other case is as sorry, there's something wrong here. Let's see, a square. Yeah, sorry, it's actually an unstable node. Yeah, it's yeah, so it's just flowing out, and this is the case when a square is less than b square. So now what is happening here is, depending upon what's your initial condition, their love just grows or it ends into eternal void, right? Okay. Now, so this was identical. Okay, so let's take a case of a let's take this case. What is this an example of? Now the lovers are non-identical. So Romeo is an eager beaver. What is Jay's style? She is a cautious lover. Okay, if there is no signals coming from Romeo, she quickly suppresses her feelings. Okay, but if there is signal coming from Romeo, she reciprocates. Okay, so what will happen if you have a situation like this? Okay, so again for simplicity, let's take J equal to A B, and this is B minus A. What? So trace is 0. What is determinant? Minus a square minus b square, right? So that's negative, right? So determinant is here, you are on this line. So basically again a saddle. Okay. So this is when you can have completely different styles of lovers, but even that you can analyze. Okay. Now interesting case where you have Romeo, Juliet. Okay. So, and this is usually the fate of many single male. They are cautious lovers. Okay. Okay, so far it looks like two cautious lovers approaching each other, but now the problem is this is 0. So now what will happen? Sorry? Yeah. No R meaning? Yeah. So the J is, the matrix is, so cautious lover, right? So it's minus A, then
Lastly,
0, then B and minus A. Okay. So what will happen? Huh? Is it? What is trace? Trace is negative. Okay. So you are on this side. What about determinant?
Positive.
Determinant is positive. So you are on this quadrant, right? And you know that you are not here, okay? So you are on a stable node, that is, it will go to 0 0, okay? But here's an interesting part. Yes, the fixed point is stable, but if you look at the flow line, and this is where actually looking at the phase plane is sometimes going to give you some interesting clues which just doing fixed point analysis won't do you, like, you know, Aninda was mentioning that you can just look at the phase plane and look at the vectors. So this is R, this is J, right? Now in both cases along this axis you have things flowing down, except that Romeo has this issue that if there is any signal from J, okay, then he starts getting interested, right. So what does that mean? That means if J is in any way positive, there is a flow towards the right, okay. But if there is no signal, it just basically flows back. So what you will see is that starting from absolutely 0, if there is any signal from J, there is an initial flow to positive side before it goes back. So there is a transient behavior, an initial transient growth which then falls. So if you look at Romeo's love, it basically rises like this before going back. So if you are interested in not just the asymptotic behavior, but also the initial transient behavior, you can see that there could be some interesting behavior which the fixed point does not give you any clue about. So this can be obtained by looking at the phase portrait, which is what Shashi and Aninda were talking about. Like, instead of just doing fixed point analysis, you can also look at the flow diagram on the phase plane. So you can just look at the vectors, flow vectors, okay. Okay, so I leave you as an homework. Yeah.
In the stable node, unstable node, all the length is straight, right?
Yeah, so I mean there could be some flow line depending upon, yeah, so in the identical level case it will all be straight. If A and B are not exact, if the cases are not exactly the same, so there will be some curvature in the flow lines, because if you look at the vectors are made out of two components, right, in each point. One is given by Romeo's love for Juliet and the other given by Juliet's love for Romeo, or Romeo's component and Juliet's component. And so looking at the summation of the vectors, you make up these lines. So if these values are not the same, there could be curvature in these lines, because the arrows could be not, instead of just 45°, they could have different alignments, okay, that is why, and so on. Okay, so I leave you as an homework the following problem. This is what I call the Shelley affair. Anybody know the name of Percy Bysshe Shelley, the famous romantic poet? Yeah. So he married the daughter of James Goodwin, and her mother was Mary Goodwin, I think, Mary Wollstonecraft, the famous woman's libber. So Mary Shelley was their daughter, and story goes that Shelley was a guest in their house, and he was already married. So his first marriage was also a cause célèbre, because he eloped with his wife to Scotland and to get married. Now he is already married, he already has child. He goes to Godwin's house and he looks at, like, to him James Godwin is a god, because he is writing all these books on socialism and so on. Mary Wollstonecraft is also writing Vindication of the Rights of Women and so on, and he sees their daughter, like, and Shelley like completely falls head over in heels in love with Mary Shelley. So, but the interesting point is, many biographers of Shelley said that Shelley was not so much in love with Mary as the idea of being in love with the daughter of such famous people, right? And so I call the Shelley love affair as something like this. So this is Percy Bysshe Shelley, and this is Mary Shelley. So Mary is of course very cautious, Percy Bysshe Shelley, on the other hand, is completely in love with the idea of being in love with Shelley, Mary Shelley, right? And so, so whereas Mary is of course flattered by the fact that Percy Bysshe Shelley was already pretty famous as a romantic poet, that such a famous poet is paying such attention to her. Now, it doesn't matter actually whether she reciprocates it or not. Percy Bysshe Shelley is so much in love with this idea of being in love that he's completely indifferent to what Mary Shelley thinks. So you can work this out, what will eventually happen to this love affair. Okay, sorry Anindya, I'm now really feeling so guilty that I can't really go on beyond this.
No, please go ahead. I mean, who would have thought that there is so much to learn about love in this conference? So, please continue.
Shakti, is there any possibility that I can have another lecture at some point? No, I know, maybe not today. Can we eat into someone else's talk some other day?
We'll have to ask someone.
Sorry?
We'll have to ask, or we can extend one session from 5 to 6 on Monday.
Yeah, maybe we'll do that. No, Anindo, I'm really feeling guilty now. Okay. Okay, so I'll stop at this point because this is a very natural stopping point, because next would have been the nonlinear system. I really do need to do this before Shagod starts his talk, because this will give us some of the important concepts that he will be using. So I can't let go of that lecture either, but this will act as the launching pad for understanding now what will happen if I go beyond linear to nonlinear. What you have learned so far will be very useful, because what we will see is with that we will be linearizing about the fixed points of the nonlinear system and try to understand what is going on around the fixed points. Now you might say, why do that? Let us try to understand the whole nonlinear system. Unfortunately, that turns out to be very difficult. Okay.
Even within linear, you don't make A and B functions of time.
A good point. So if you have a explicit time dependence, then you get what are known as non-autonomous systems. Okay. So far we have been dealing with autonomous systems which don't depend explicitly on time. None of the parameters depend explicitly on time. If parameters start depending explicitly on time, then actually it becomes a higher dimensional system, because you can think of the time as another variable, dt by dt equal to 1. Yeah, so now you can have chaotic behavior, because once you go to higher dimension, we know other behavior is possible. So something I didn't talk about is, why is it that oscillation is the only thing which is possible here and not chaos? Okay, and that again has to do with the fact that trajectories cannot cross. Okay, so if you have a system, if you have a two-dimensional system, what are the different things we are capable of? We can go completely diverge, we can converge. Okay, even the saddle is like basically diverging, so I don't distinguish the saddle. But there is a third possibility, which is I am going around in a closed curve. Right? I can't go do anything beyond that. Why? Because suppose I say I will do like this. The moment I do this, I am basically crossing here, and you will see that now we will have at that point two different directions of the flow, which is not allowed by this single valued nature of a functions. Okay. And so therefore, if you look at a chaotic orbit which looks like this, there is no way we can have this kind of a trajectory in a two-dimensional system. Okay. Once in 3D, these kinds of things become possible. And so you will see that many two-dimensional systems, once you introduce an explicit time dependence like sin omega t or something, can actually become capable of showing chaotic behavior. So it does not mean that you are seeing chaos in a 2D system, it simply means that because you are introducing explicit time dependence, time becomes an effective third variable. And so in a three-dimensional system, chaos is possible. Okay. So with that, I will stop and thank you.